Hello. In this video we will explore the concept of an antiderivative of a given function. As you will see, antiderivatives will be important next quarter when you study integral calculus. Our focus here is to introduce this idea now as a prelude to what you will do next quarter in earnest. Let's review what we've been doing this quarter. Let's start with a function, say f of x equals x squared, and take the derivative. We use the operator d dx to represent the act of taking the derivative. And we write the derivative with respect to x of x squared equals 2x for the derivative function. In this context, it is helpful to think of the function being differentiated as the parent. Here it is f of x, which is x squared, and the derivative function as the child. But what if we want to reverse the process above? Given a child function, let's say f prime of x equals 2x, what is the parent function? We see that we immediately run into a problem. There are many functions whose derivative is 2x. For example, x squared plus 1, x squared plus 2, and so on. It is clear that each derivative function will have an infinite family of parent functions, all differing by a constant c. Thus, if f prime of x is 2x, we will write f of x equals x squared plus c to represent the family of parent functions of the function f prime of x equals 2x. So here we have f prime of x as the child, and then f of x as the parent family, or the family of parents. In the context of operators, what operator symbol should we put above our arrow up here to indicate the process of reversing the derivative? We will say that the process by which the parent family is computed given a child function is called integration, and use the elongated s symbol for the operator, which looks like this. We will write the integral of 2x with respect to x is equal to x squared plus c to represent the family of parent functions of the function 2x. The notation, the integral of 2x with respect to x, is called an indefinite integral, and it represents the family of all parent functions of the function 2x. Since the functions of the form x squared plus c form this family, we will use the indefinite integral to represent this family. Remember to include the dx at the end of the indefinite integral. This is needed just as it is needed when we write d dx for the differential operator to mean the derivative with respect to the variable x. The dx in the indefinite integral means that we are integrating with respect to the variable x. Now, starting from the child function, we could write f prime of x for this function, but since the child is just a function, we will often let a small case letter like small case g to represent the child function, say g of x. But how will we write a parent of g of x? If a small case letter is used for the child, then it seems reasonable to let a capital letter represent a parent function. For example, a big G. So if g of x is a child, then a parent of g of x would be written as capital G of x. And the way we test that g of x is a parent of little g of x is by taking the derivative. The use of the capital letter G to represent a parent of the small letter function g leads us to the definition of antiderivative. So we say definition an antiderivative of a function small g, a child if you will, is a function capital G of x such that, so how do we know capital G is the parent? We check g prime of x is equal to little g of x, the child. So in the language of the definition above, an antiderivative of lowercase g of x equals 2x is uppercase g of x equals x squared. So if g of x is 2x, then an antiderivative of that function is x squared. Keep in mind that the phrase an antiderivative means one of the family of all antiderivatives of the lowercase function little g of x. To represent the entire family of antiderivatives, the parents, we write g of x plus c to represent the family of all antiderivatives of g of x. So in general terms, we will write the indefinite integral of lowercase g with respect to x is equal to capital G of x, one antiderivative from the family, plus a constant for the whole family. With this all in mind, we're ready to start computing antiderivatives of some simple functions. So let's do a couple of examples. In each case, we're going to find an antiderivative capital G, so that's one function from the family of antiderivatives, for each little g given in each part. So for problem number 1, if g of x is equal to x, well, capital G of x will be a function whose derivative is equal to x. We might start with x squared, but then we know that when we differentiate, we get 2x. So to get rid of that unwanted 2, we put a 1/2 in front, and then we can check, take g prime of x, and that's 1/2 times 2x, which is equal to x. So big G is a parent of little g. In problem 2, so the same idea applies. In the first problem we saw that we added 1 to the exponent and divided by 2, so let's see if that works in the second example. Following the pattern in problem 1, we might want to write x cubed over 3, and then we can check when we compute g prime of x, we get 1/3, and then the derivative of x cubed is 3x squared. And sure enough, the 3's cancel and we get x squared. So that checks too. And similarly for the third problem, capital G of x following the pattern, x to the 4th over 4, and you can check that g prime does indeed equal x cubed. And so in problem 4, we might be inclined to write a general formula. We might want to write g of x is equal to, again following the pattern, x to the n plus 1 over n plus 1. And if you take the derivative, g prime of x as a check, well, 1 over n plus 1 is just a constant, so we bring the constant forward, and then we differentiate x to the n plus 1. Well, that's going to be n plus 1 times x to the 1 less than n plus 1, but that's n, and these cancel, and we get x to the n, and so we see that that works for all positive integers. Seems to be a general pattern. The fifth problem is a little trickier because if we're going to kind of follow the examples we've looked at so far, we've sort of run into a roadblock here because this is not x to a power. But we could write this as a power if we use algebra. And so I might want to write this algebraically as x to the 2/3. Now, we've kind of shown that for positive integers, this formula seems to work when we have x to a power. So we might want to use that in this example and just see what happens. So let's take x to the 2/3. So sort of following the pattern. I think I'll write this over here. Well, if we take if we add 1 to the power, well, 2/3 and 1, that's 1 2/3, so that's 5/3. And then we would divide by that same power. But 1 over 5/3 is 3/5, so I could write this as 3/5 times x to the 5/3. We should probably check this, so if we take g prime of x as our check, then we'll have our 3/5, and then we differentiate x to the 5/3, and we get 5/3 x, 5/3 minus 1 is 2/3. The 5's cancel, the 3's cancel, we're left with x to the 2/3, and that's the function we started with, so that does work. And so you can use the pattern in the last problem, in problem 4. Highlight this here. This ends up becoming a general rule wherever it's defined. So not only does it work for positive integers, but it works for any real number. And you can see the only real number where it wouldn't work would be when n is equal to -1. And that's a special case that you'll learn later when you study the book. So that one you'll learn later on. We won't discuss that now in this brief introduction. In problem 6, let me just remove problem 7. So now you might be inclined to take the derivative here, but if you differentiate the cosine, you get negative sign. I'm looking for a function whose derivative is cosine. So remember, you're working backwards here. We're undoing differentiation. So you might guess correctly that g of x is equal to the sine of x, although this often creates lots of problems for students because often students will differentiate the cosine instead of integrating the cosine. If we differentiate the cosine, we get g prime of x is equal to negative sine of x, not sine of x. And so we can compare and contrast that with g of x equals the sine of x. This one's a little trickier. Again, g prime of x is cosine x, but remember we're working backwards. We want a function whose derivative is sine of x. So you could pause this for a moment if you want and see if you can write down the correct answer and then start it up in a second. I'm just wait a moment here to let you pause it. And so if you're following this correctly, a function whose derivative is sine, since the derivative of cosine is minus sine, would be minus cosine x, the antiderivative. And then we can check when we take g prime of x, we take the negative of the derivative of cosine, which is minus sine of x, and that's equal to sine of x, and so that does check. So you got to be really careful when you're taking integrals of the sine and the cosine. People often differentiate them when they should be integrating, and don't make that mistake either. And so finally, if we continue with problem 7, since we found n antiderivative, if the problem asks to find all the antiderivatives of g of x equals the sine of x, in that case we write the family down and we would write capital G of x is equal to minus cosine x plus c. So we want to represent the family of all antiderivatives. We'll add the constant in there to represent the whole family of antiderivatives of the sine function, namely the minus of the minus cosine x plus c is the family of antiderivatives of sine x. So that's a short introduction, but that will get you started with working with antiderivatives.